Okay, let's dive into this. When you think of Mars, what exactly comes to mind? A freezing, barren red rock millions of miles away that looks like, well, a pretty terrible place to take a vacation, right? It just feels entirely alien? But today, in this explainer, we're going to look at the data and discover a truly surprising reality. Mars is actually remarkably similar to Earth. In fact, out of the entire solar system, it is uniquely equipped to serve as humanity's second home. We're going to explore the astonishing parallels between our blue marble and the red planet and see exactly how these similarities are going to shape the future of human settlement. Think of this as our mission briefing for today. We'll start with Section 1, the Martian Null Hour. Then we'll move into Section 2, Seasons in the Sand, explore Section 3, a surprisingly spacious planet, dig into Section 4, the power of volcanism, and finally finish up with Section 5, terraforming the red planet.
So, starting with Section 1, the Martian Null Hour. Let's talk about daily life on Mars.
Now, what's really interesting about this is before we can even talk about building sprawling cities or terraforming atmospheres, we absolutely have to look at the immediate, everyday human experience. What are future colonists going to face from the moment they wake up? Well, one of the most astonishing things about Mars is its rotation. It actually causes the Martian day to be almost exactly the same length as our Terran day right here on Earth. The sun is going to rise and the sun is going to set, basically just like it does outside your window right now. To handle the very slight difference in time, mission planners are proposing structuring the Martian day exactly like an Earth day, but adding in what they call a null hour. It sounds super sci-fi, but it's basically just a free period at the end of the day to perfectly synchronize our watches with the planet's rotation. Because get this, the difference is just 37 minutes. That is the entire difference between a day on Earth and a day on Mars. A Martian day is 24 hours and 37 minutes long. Think about how incredibly small that is in the grand scheme of things. It's literally a tiny fraction of our waking lives. Imagine just getting an extra 37 minutes to sleep in or read a book or just relax every single day. For a future colonist, this is a massive deal because it means they won't need to drastically alter their internal biological clocks. No one has to deal with permanent, massive jet lag. Our circadian rhythms, which took millions of years to evolve on Earth, will map almost flawlessly onto the natural rhythm of Mars. To really appreciate how lucky we are with that 37-minute difference, let's just quickly compare it to other viable targets out there. On Mercury, a single day lasts 1,400 hours. On Venus, you are waiting 5,800 hours just for the sun to set. Even on our own moon, a single day-night cycle takes a full 30 Earth days. If we tried to colonize any of those places, the rising and setting of the sun would happen at these agonizingly long intervals. Human societies would struggle immensely with that. We'd basically require constant artificial lighting, essentially forcing colonists into a depressing, permanent cave or tunnel existence. Mars perfectly avoids this psychological nightmare because natural lighting will come and go at wonderfully Earth-like intervals.
Section 2, Seasons in the Sand. Let's scale up to Martian climate cycles.
Zooming out from the daily cycle to the yearly cycle, we find another really profound similarity. And this brilliantly illustrates the point: axial tilt. Earth tilts at 23 degrees, while Mars tilts at 25 degrees. Now, why does that matter? Because seasons are dictated by a planet's tilt, not by its distance from the sun. If a world had a much greater tilt, the seasons would be violently extreme. If it had almost no tilt, you'd have no discernible seasons at all, just a static, monotonous climate. But because Mars is tilted at almost the exact same angle as Earth, it's actually going to experience spring, summer, fall, and winter. Future colonists will have discernible, familiar seasons, just like we do at home.
Moving right along to Section 3, a surprisingly spacious planet. We're looking at usable land surface here.
We've zoomed out from the daily clock to the yearly calendar, and now let's zoom out to the geographical scale to ask a really crucial question. Just how much room do we actually have to live and build on Mars? Well, to answer that, we first have to look at ourselves. We all know Earth is a blue marble, right? Approximately 71% of Earth is covered by oceans. We live on a water planet, meaning we are strictly confined to that remaining 29% of land. Keeping that in mind sets up a truly surprising realization about Martian geography. So the crucial point is this: even though Earth is physically a much, much larger planet than Mars, their actual land surface areas are incredibly similar today. Why? Simply because Mars has no oceans right now. But it actually goes a step further. Currently, a huge chunk of Earth's land is vast tundra and subarctic forest, areas that are only marginally usable for large-scale human civilization. If humans end up controlling the eventual terraforming and warming of Mars, its Arctic regions might end up being surprisingly small.
This suggests that even if Mars gets a small ocean in its future, the total amount of comfortable, usable land could potentially be greater than what we have right here on Earth. Wild, right?
Section 4. The power of volcanism. This is all about ores and resources.
Now we're shifting to the industrial scale. Human civilization absolutely requires materials. We need iron, aluminum, and gold to build habitats, electronics, you name it. Well, it turns out Mars has a rich volcanic past that acts like a giant geological sorting machine, making it literally the absolute best place in the solar system to plant our first off-world colonies. Here's exactly how it works. When a planet has magma, that intense heat cooks what geologists call undifferentiated rock. Because elements like gold and iron have totally distinct properties, they melt and then solidify at different times and temperatures compared to the surrounding rock. This geological sorting process gathers these useful metals together, creating concentrated, rich veins of ore that human beings can actually mine and use.
To truly understand why this is such a game changer, let's briefly bring back the moon as a negative contrast. The moon does not have this volcanic history. This creates what we can call the lunar problem. Because the rock up there is undifferentiated, you might find a rock that contains, say, 0.1% of gold. But that gold is permanently scattered as tiny microscopic traces throughout millions of tons of totally useless dust. Without the intense heat of volcanoes to sort and concentrate those elements into veins, mining on the moon for essential industrial metals is practically impossible. Mars's volcanic history, on the other hand, transformed useless rock into the vital resources a colony needs to survive.
And speaking of Mars's volcanic history, I absolutely have to share this awe-inspiring metric with you. 16 miles. Or 25 kilometers. That is the height of Olympus Mons, the tallest volcano in the entire solar system, and it's sitting right there on Mars. That is roughly 2.5 times the height of Mount Everest. To put that insane scale into perspective, because Mars has such a thin atmosphere, the peak of Olympus Mons literally reaches right out into space. It is a towering physical monument to the violent geological history that inadvertently prepared the planet for human industry.
Section 5. Terraforming the Red Planet. Let's move to and see how this builds toward a warm, wet world again. All of these built-in advantages we've talked about point toward a highly speculative, yet deeply plausible, ultimate vision for human settlement. We essentially have an incredible recipe for bringing an entire planet back to life. The data tells us for sure that Mars was once a warm and wet world. And crucially, we know there is still a ton of water there today. It's just locked away in ice. Because we understand atmospheric science, we know that the deliberate accumulation of greenhouse gases could actually be used to raise the planet's average temperature. By warming the planet up, that abundant trapped water could be put right back into an active atmospheric circulation. So while Mars today is a cold, dry desert, there are existing or near-horizon scientific solutions to transform it back into a warm, wet world. Which brings us to our final thought for today. We've seen the data, right? From the 24-hour and 37-minute days that flawlessly match our internal clocks, to the familiar seasons dictated by its tilt, to a potentially massive amount of usable landmass and a volcanic history that literally sorted the exact ores we need to build, Mars is not just some random rock in space. It is remarkably equipped to become humanity's second home. The environment is waiting, the science to warm it up is pretty well understood. So the real question we have to ask ourselves now is this. Are we actually prepared for the incredible technological and human challenges of getting there? I hope this explainer has sparked your curiosity about our multiplanetary future, and I really encourage you to keep exploring the realities of making Mars our home.